Hello everyone, in this lecture I will solve different problems in energy and energy transfer. Just to mention that this lecture is a supportive material for a previous lecture. The link for that lecture will be found in the comments. A constant force of 12 newtons in the positive x direction acts on a 4 kilogram object as it moves from the origin to point 6i minus 8j in meters. How much work is done by the given force during this displacement? So in this case here, F it's equal to 12 newtons, and the displacement starting from the origin, it's 6i delta x equal to 6i minus 8j. Therefore, the work in this case equal to F dot D. In other words, work equal to 12 I hat, because the force in the positive x direction, but 6i 8j, in this case work equal to 72 joules. A 5 kilogram object is pulled along a horizontal surface at a constant speed by a 15 Newton force acting 20 degrees above the horizontal. How much work is done by this force as the object moves 6 meters? Now in this case here we have an object, it's 5 kilograms, and there is a force acting on this object making a 20 degrees with the horizontal, and the force itself is 15 newtons. Now the work in this case it's equal to F dot D, or equal to 15, this is the force, and it's in this direction here, times 6 is the displacement here, cosine the angle between the displacement and the force, 20. You do the math here, you will find it's 90 cosine 20, or in other words, work equal to 84.5 joules. A 2 kilogram projectile moves from its initial position to a point that is displayed 20 meters horizontally and 15 meters above its initial position. How much work is done by the gravitational force on the projectile? Now the object moves 20 meters like this one here, and moves 15 meters in the vertical direction. This is the 15 meters. To find the work actually equal to minus delta U, in such a way U here is the gravitational potential energy, or U initial minus U final. The initial gravitational potential energy equal to 0 because the initial height equal to 0, so in this case work equal to minus mgh. M in this case it's equal to 2, g is gravity acceleration, it's 10, and h here equal to 15. In total the work equal to minus 300 joules. How much work is done by a person lifting 2 kilogram object from the bottom of a well at a constant speed of 2 meters per second for 5 seconds? Now, since the required work is done by the person, in this case here, work actually equal to delta U. It's not minus because it's done by the person. Now, to find the work here, we actually need to find the x final. So x final here equal to x initial plus v initial t plus half a t square. Since the object is moving with constant speed, In this case, this part here it's equal to 0, assuming x initial equal to 0 as well. In this case, so x final equal to v initial equal to 2 times time 5 or equal to 10. So the work in this case here equal to u final minus u initial, or mgh. M in this case it's equal to 2 times 10 times h here equal to 10, or in other words equal to work equal to plus 200 joules. A 2 kilogram particle has an initial velocity 5I minus 4j meter per second. Sometime later, its velocity becomes 7I plus 3j meter per second. How much work is done by the resultant force during this time interval, assuming that no energy is lost in this process? Now, V initial equal to 5I minus 4j. Now, the magnitude for V initial, it's equal to square root of 25 plus 16, or in other words, equal to square root of 41. Now, V final equal to 7I plus 3j. In this case, the magnitude for V final equal to square root of 49 plus 9, or in other words, equal to 58. Now, work, on the other hand, total equal to delta K. And in this case, it's equal to half the final square minus half the initial square. This is work total. Now, you substitute numbers. In this case, half m in this case equal to 2 times square root of 58 square minus half 2 square root of 41 square. You substitute work total in this case equal to 58 minus 41, or in other words, it's equal to 17 joules. A block is pushed across a rough horizontal surface from point A to point B by force with magnitude equal to 5.4 Newton, as shown in the figure. Now, the magnitude of the force of friction acting on the block between point A and B is 1.2 newtons, and points A and B are 0.5 meters apart. If the kinetic energies of the block at A and B are 4 and 5.6 respectively, how much work is done on the block by the force P between A and B? Now we need to find the work done by the force P in this case here, and we have the initial and final kinetic energies. Remember, work total in this case here equal to delta K, or K final minus K initial, and K final it's equal to 5.6 minus K initial, it's 4. In other words, work total equal to 1.6 joules. Now, work total, this one here, actually we have work from friction and work from external force. In this case, it's P, and this total work here, it's equal to 1.6 joule. Now, work from friction plus work from force P equal to 1.6, or work from friction, this one here, frictional force equal to 1.2 newtons. The distance between points A and B are 0.5, in this case it's equal to 0.5, and the angle between the force and distance it's 180 degree, cosine 180 it's minus 1, plus work done by force P equal to 1.6, and move this part in here. So work from P equal to 1.6 plus 1.2 times 0.5, or in other words, it's equal to 2.2 joules. And this is work from force P. A constant force of 15 newtons in the negative y direction acts on a particle as it moves from the origin to the point 3i, 3j minus 1k. How much work is done by the given force during this displacement? Now, based on the given information here, the force actually equal to 15 newtons and in the negative y direction, so j hat with minus sign. And the displacement here equal to delta x equal to 3i, 3j minus 1k. Now the work actually it's equal to F dot D, and in this case it's equal to minus 15 j hat dot 3i plus 3j minus 1k. Now, as we all remember that when you dot product two vectors, you only just multiply I with I, j with j, k with k. So in the force, there is no I, no k. So in this case, you just multiply this one with this one, and that's it. So the work here, it's equal to minus 45 j hat with j hat is just 1 joules. So the work here equal to minus 45 joule. A body moving along the x-axis is acted upon by force Fx that varies with x as shown in the figure here. How much work is done by this force as the object moves from x equal to 1 to x equal to a? Now, based on this graph here, this is 1 here, and this is 8. It's right here. Now, to find the work done by this, you just chop this curve into known shapes, like this one here. And remember, work done by a force is actually the area beneath that curve. Now, the area for this one, you can chop it into two pieces. This one here, let's name it 1, and this is 2, and this is 3, and this is 4. Now, work actually, it's equal to the area beneath the curve 1, which is in this case, it's a rectangle. The area for the rectangle, it's equal to the width times the length. Now, the width actually equal to 3, 1, 2, 3, and the length equal to minus 8. So it's equal to minus 24. Now, the area for the second part, it's a triangle, and the area of the triangle have the base times the height, and the base here it's equal to 2, and multiply by half is just 1, times the height for this triangle is minus 8, plus minus 8, plus. Now, again, we have here triangle, and the area for this triangle, half the base it's equal to 1, so it's half, multiplied by the height of this triangle, it's equal to 4. In this case, 4 times half, it's just 2, plus. Now, this is a rectangle with length equal to 4 and width equal to 1. So 4 times 1 is just 4. In total, the work done by this force is equal to minus 26 joules. A force acting on an object moving along the x-axis is given by 14x minus 3x squared newtons, where x it's in meters. How much work is done by this force as the object moves from x equal to -1 to x equal to +2? This force is not constant force. We have to integrate. So work actually equal to integration from x1, which is -1, to x2 equal to 2f dot dx. Now you integrate this one here. You will find integration -1 to 2, 14x minus 3x squared dot dx. No need, by the way, for the dot here. And work equal to 14x squared over 2 minus 3x cubed over 3, from -1 to 2. Now work actually equal to 7x squared minus x cubed minus 1 to 2, and you substitute here. It's equal to 28 minus 8. When you substitute by 2, by the way, minus, when you substitute with -1, it's 7 plus 1, and equal to 20 minus 8, or 12 joules. The force an ideal spring exerts on an object is given by Fx equal to minus kx, where x measures the displacement of the object from its equilibrium position, x equal to 0. If k, which is the spring constant, equal to 60 Newton per meter, how much work is done by this force as the object moves from x equal to 0.2, this is actually 0.2, to x equal to 0. Now in this case, remember here, the work done by this force, in this case, work actually equal to minus delta U spring, or half k x1 square minus half k x final square. In other words, half k, in this case it's 60, and x equal to 0.2 square minus half 60 x final, here equal to 0. Now equal, in this case, 30 times 0.04, or in other words, it's equal to 1.2 joules. This is the work done by this force, and by the way, this force is actually spring force. A 4-kilogram block is lowered down a 37 incline, a distance of 5 meters from point A to point B. A horizontal force F equal to 10 newtons is applied to the block between points A and B as shown in the figure. The kinetic energy of the block at A equal to 10 and at B equal to 20 joules. How much work is done on the block by the force of friction, this one here, between points A and B? Now let's see. The force here, this one here, when we analyze the force, remember, when we actually take the angle with the tail. So in this case here, the force, this one, the force, if this is 37, this will be 37 as well. So you analyze the force, it's F cosine 37. Now remember, the weight is actually directed to the center of the earth. You analyze the mg here, you will get mg cosine theta, and this one here, mg sine theta. Again, work total equal to delta k, or in other words, equal to 20 minus 10. This is actually work total. Now let's find out the forces that creates this work, we actually have external force, work from F. We also have work from gravity and work from friction. And that's what we actually look for, this one here. So work from F plus work from gravity plus work from friction, it's equal to this one here. 20 minus 10 is equal to 10. Now work from F is equal to minus 10 cosine 37, and remember this minus here because the displacement directed this way here and the force directed this way here. The angle between the displacement and the force of cosine 37 is equal to 180, and cosine 180 it's equal to minus 1. So minus 10 cosine 37 plus mg sine theta, it's actually equal to 40 because the mass equal to 4, g equal to 10, and sine 37 it's 0.6 here, plus work from friction, that's what we're looking for, equal to 10. Rearrange this equation, work from friction equal to 10 minus 80, or in other words almost 70 joules. As a 2 kilogram object moves from 2I plus 5j in meters to 6I minus 2j in meters, again the constant resultant force acting on it is equal to 4I minus 3j newtons. If the speed of the object at the initial position is 4 meters per second, what is its kinetic energy as its final position? Again, work total here equal to delta K, and in this case here half m v final square minus half m v initial square, and the only force creating work in this case is just F. So this one here just F, work from F, and work here from F it's equal to F dot D and equal to F 4I minus 3j, and D in this case it's equal to 6 minus 2 4I minus 2 minus 5 minus 7j. Now you do this here, you will find it's 16 plus 21. You just multiply I with I and j with j. 4I dot 4I it's 16, and minus 3j dot minus 7j it's equal to 21, and in total it's equal to 37. Now 37, this one here, back to this equation, the original one, this one here, 37 it's equal to, this is K final minus half times 2 times 4 square, this one here 16. You do the math, K final equal to 37 plus 16, in other words it's equal to 53 joules. A block slides on a rough horizontal surface from point A to point B. A force with magnitude equal to 2 newtons acts on the block between points A and B, as shown in the figure. Points A and B are 1.5 meters apart. If the kinetic energies of the block at A and B are 5 joules and 4 joules respectively, how much work is done on the block by the force of friction as the block moves from point A to point B? Again, work total equal to delta K, and K final in this case it's 4 and K initial it's 5. So work total here equal to minus 1. And in this situation, we actually have two forces, work done by the friction and work done by the force P. In this case, work from friction, that's what we are looking for, plus work done by force P. Now, if this is P here, now, so work done by P, it's equal to P cosine 40 times the displacement, in this case, equal to 1.5, equal to minus 1. So work from friction, it's equal to minus 1 minus 2.31, or work from friction equal to minus 3.3 joules. A 2 kilogram block slides down a frictionless incline from point A to point B. A force with magnitude P equal to 3 newtons acts on the block between point A and B as shown. Points A and B are 2 meters apart. If the kinetic energy of the block at point A is 10 joules, what is the kinetic energy of the block at point B? Again, work total equal to the kinetic energy at B, this is missing, minus 10. Now we have here in this situation, we have work done by gravity and work done by the external force. In this case, it's P. Now, by the gravity, remember when you analyze the weight, this is weight mg, this is mg cosine theta, and this is mg sine theta. Work done by the gravity, it's mg sine theta, this is the force, and the displacement, in this case, it's 2, it's a plus. Now P, the force here, times 2 times the angle between P and the distance and the force, it's 180. So cosine 180, it's minus 1. That's all equal to the kinetic energy of the block B minus 10. Rearrange this one here. The kinetic energy at point B equal to 14 plus 10, or equal to 24 joules. A 6 kilogram block slides along a horizontal surface if mu k, the coefficient of kinetic friction, equal to 0.2 for the block and the surface. At what rate is the friction force doing work on the block at an instant when the speed equal to 4 meters per second? Now we have a block here, and we have mg, and we have normal. In this case, the frictional force, it's actually equal to mu k times n, and n in this case is the normal force. And remember, on this one here, sum of all forces on y equal to 0, so mg minus normal equal to 0, so mg equal to normal. So the normal for this case, it's equal to mg. Now F, or the frictional force, it's equal to 0.2, this one here, it's mu k times n, in this case mg, m equal to 6 and g equal to 10, so 6 times 10, so F almost equal to 12 newtons. Now the power equal to F dot V, and in this case it's equal to 12 times 4, or in other words, it's equal to 48 watt. A 2 kilogram block slides down a plane inclined at 40 degrees with the horizontal at a constant speed 5 meters per second, at what rate is the gravitational force on the block doing work? Now we have here the situation, we have an inclined surface like this one here, and we have a block located somewhere here, and this is 40 degree is the angle of the inclined surface. Now we have the weight, this mg, and we have here mg cosine theta, and we have mg sine theta. Now for this case, F is the force of gravity equal to mg sine theta, and P power equal to F dot V, or in other words, mg sine theta dot V, in this case it's 5, or 20 times 0.64 times 5, or equal to 64.3 watt. A 1.6 kilogram block slides down a plane inclined 25 degrees with the horizontal at constant speed 2 meters per second. At what rate is the frictional force doing work on the block? Now again, same situation as before, this one here. Now this is 25 degrees, and we have a block here, and the weight mg and mg cosine theta and mg sine theta, and this is the normal force. Now F is the frictional force, should be equal to mg sine theta with minus sine, so it's equal to 16, because m equal to 1.6, g equal to 10 sine 25, and don't forget the minus sign, so F here equal to 6.72 with minus sign. So the power in this case, it's equal to F dot V, and V in this case it's equal to 2, so minus 672 times 2, or in other words, it's 13.4, don't forget the minus, watt. A 3 kilogram block is on the horizontal surface. The block is at rest when at t equals 0, a force of magnitude 12 newtons acting parallel to the surface is applied to the block, causing it to accelerate. The coefficient of kinetic friction between the block and the surface is 0.2. At what rate is the force P doing work on the block at t equal to 2 seconds? Now again, we have a block here on horizontal surface with 3 kilogram the mass, and this is the force 12 newtons. So sum of all forces equal to ma. Now F minus frictional force, it's equal to ma, or 12, this is force F, minus mu k n equal to ma. You substitute things here, you will find that 12 minus 0.2 times 30, in this case, equal to 3a, and a in this case equal to 2 meters per second square. Now V final equal to V initial plus AT. Now you substitute the acceleration back in this equation here, you will find the final velocity equal to 2 times 2, or 4 meters per second. The power, in this case, it's equal to the force P dot V, and the force P, it's 12 in this case, times 4, or equal to 48 watt. A 10 kilogram block on horizontal frictionless surface is attached to a light spring, force constant 1.2 kilonewton per meter. The block is initially at rest at its equilibrium position when a force magnitude P acting parallel to the surface is applied to the block, as shown. When the block is 8 centimeters from the equilibrium position, it has a speed of 0.8 meter per second. How much work is done on the block by the force P as the block moves the 8 centimeters? Now this block here, because of the force P, will move this way here like this, will be somewhere in here, and the distance, this one here, from the initial position, it's 8 centimeter in this case here. So work total equal to delta K, or equal to half V final square minus half the initial square, and this one here, it's equal to 0 because the object initially at rest. Now work total, we actually have here work from spring and work from force P. Now work from spring plus work from force P, it's equal to half the final square minus half kx square. And remember, the initial position is equal to 0 at the relaxed, so the potential energy of the spring at the relaxed position equal to 0 plus work at point P equal to half V final square. Now work P equal to half 10.8 square plus half 1.2 10 to the power 3, this is K, and don't forget to convert centimeter into meters, so 0.08 square, and you will find work at point P equal to 3.2 plus 3.8. In total, it's 7 joules. The horizontal surface on which the block slides is frictionless. The speed of the block before it touches the spring is 6 meters per second. How fast is the block moving at the instant the spring has been compressed? 15 centimeters. K in this case, it's 2 kilonewton per meters. Now work total, again, this is the most important equation we have. Work total equal to delta K, and we only have here work done by the spring, nothing else, so equal to half the final square minus half the initial square. Now again, half the final square equal to minus half work done by the spring, kx square, plus half the initial square, half times 2 the final square equal to minus 2000 because it's 2 times 10 to the power 3, this one right here, 0.15, and we actually convert the centimeter into meters, square plus half, 2 is the mass in this case, and 6 square, 36, or minus 1,000 times 0.15 square plus 36 equal to V final square minus 22.5 plus 36 equal to V final square, or 13.5. This is V final square. V in this case is equal to square root of 13.5, or V equal to 3.7 meter per second. A 2 kilogram block situated on a frictionless incline is connected to a light spring with spring constant K equal to 100 Newton per meter. As shown, the block is released from rest when the spring is unstretched. The pulley is frictionless and has negligible mass. What is the speed of the block when it has moved 0.2 meters down the plane? Again, work total equal to delta K, and we have actually work by the spring and work from gravity, and this equal to half m the final square minus half m the initial square. And remember, this one is 0 because the block initially at rest. Now work done by the spring, it's minus half k x square plus work done by the gravity, it's mg sine theta. This one here, remember, if this is mg, so this is mg cosine, and this is mg sine. Times the distance here, it's 0.2, equal to half 2 V final square. Rearrange this one here, V final square equal to minus 50 times 0.04 plus 2.4 V final square equal to minus 2 plus 2.4, or V final equal to square root of 0.4, V final equal to 0.63 meter per second. A 2 kilogram block sliding on a frictionless horizontal surface is attached to one end of the horizontal spring with spring constant equal to 600 Newton per meter, which has its other end fixed. The speed of the block when the spring is extended 20 centimeters is equal to 3 meters per second. What is the maximum speed of this block as it oscillates? So we have here actually a spring. We have actually a block connected with a spring, and the other end of the spring is fixed. Now, to find the maximum speed of the block as it oscillates, then work total equal to delta K, and again we only have work done by the spring equal to half m V final square minus half m the initial square. Now half k x square, and this is positive because it's the initial potential energy of the spring, and the final potential energy is 0 because it passes through the relaxed position. Now this is positive, equal to half m the final square minus half m the initial square. Now you have 600 times 0.2 square plus, you move this one back in here, half 2, 3 square, it's 9, equal to half 2 the final square. You substitute numbers, you will get 300 times 0.2 square plus 9 equal to the final square, or the final equal to square 12 plus 9, or the final equal to square root of 21. In other words, it's 4.6 meter per second. A 10 kilogram block on a rough horizontal surface is attached to a light spring, force constant 1.4 kilonewton per meter. The block is pulled 8 centimeters to the right from its equilibrium position and released from rest. The frictional force between the block and the surface has a magnitude of 30 newtons. What is the kinetic energy of the block as it passes through its equilibrium position? Now remember, work total here equal to delta K, and we have here work done by the spring, this one here, and work done by the external force, this one right here. Now this one half K x initial square minus half K x final square, and this one here 0 because it passes through the equilibrium position, plus work done by the force, it's minus 30 times 0.08, and again the minus sign because the angle between the frictional force, this one here, and the displacement is 180, cosine 180, it's equal to minus 1. Now this one here all equal to half m the final square. Rearrange this one, you will get half m the final square equal to 4.48 minus 2.4, and this one here is the final kinetic energy equal to 2.08 joules. A 1.5 kilogram object moving along the x-axis and has a velocity of 4 meters per second at x equal to 0. If the only force acting on this object is shown in the figure, what is the kinetic energy of the object at x equal to 3? Remember, work total in this case here equal to delta K, and work total in this case is the area beneath this curve. Now this is 3, the final one, it's in here. We actually have here two triangles, this one and this one here. Now this triangle, this one here, the area of this triangle, it's equal to half, and the base in this case equal to, this is 2, this one here 2, and the height is 8, and plus the area of the other triangle, it's actually, this is the base, it's equal to 1 half 1, and the height minus 4. This is equal to delta K, or in other words, this is actually equal to 8 plus minus 2 equal to half m the final square minus half m the initial square. Rearrange this one, half m the final square equal to 6 from this and this, plus half times 1.5 times 4 square, and this is actually the final kinetic energy. Here it's equal to 6 plus this one here, or in total it's 18 joules. The only force acting on a 2 kilogram body moving along the x-axis is given by this Fx equal to 2x newtons. Now where x is in meters, if the velocity of the object at x equal to 0 is 3 meters per second, how fast is it moving at x equal to 2 meters? Now again, work total equal to delta K, and in this case, since the force it's not constant, we have to integrate from 0 to 2 and F dot dx, and this actually equal to delta K, the change in the kinetic energy. You integrate this one, you will get 2x squared, because F actually it's equal to 2x divided by 2 from 0 to 2. This equal to half the final square minus half the initial square, or 4 equal to half 2 the final square minus half 2 times 9, the final equal to square root of 13, or in other words equal to 3.6 meter per second. When a ball rises vertically to a height h and returns to its original point of projection, the work done by the gravitational force is, now the work done in this case it's equal to 0. If you start from point A and move to point B and back to the same position right here, if the force is conservative, then the work in this case it's equal to 0, and the gravitational force is actually a conservative force. So to answer this question, the work in this case it's equal to 0. When a crate of mass m is dragged a distance d along a surface with coefficient of kinetic friction mu k, then dragged back along the same path to its original position, the work done by friction is, now the situation here is different from the previous example because this is a frictional force, and as we all know, frictional forces are not conservative. Then the work done when you move from point A to point B and back to the same point will never be 0 for this case. So let's see, work done by the force, it's actually to F dot D. Let's assume that the object is moving this way here. Now the displacement this direction, and the frictional force is this direction, and the angle between them it's equal to 180. Cosine 180 it's minus 1, so the work done by the force 1 here equal to minus F D, or equal to minus mu k mg d. The work done on the second path, if assuming that it's back in this one here, so the displacement this way and the force again on the opposite direction, the angle is equal to 180 degree. Cosine 180 is equal to minus 1. In this case, work on the second track it's equal to minus mu k, same mass g d. Now the total work equal to work 1 plus work 2, and both works are the same, so it's equal to minus 2 mu k mg d. It's not 0. Two balls A and B of masses m and 2m respectively are carried to height h at constant velocity, but B rises twice as fast as A. The work the gravitational force does on B is, work A equal to mgh. Now work B equal to double mass 2mgh. In this case here, work B equal to 2 work A. To answer this question, it's twice the work done on A. Equal amounts of work are performed on two bodies, A and B, initially at rest, and of masses m and 2m respectively. The relation between their speeds immediately after the work has been done on them is, now work total equal to delta K, so work A equal to half m V final A square, work B half m, it's actually 2m V final B square. If you divide these two equations, you will get work B work A equal to 2 V final B square divided by V final square A. And from the question here, the amount of work are performed on two objects is equal. It means work B divided by work A, it's 1 equal to 2 V final B square divided by V final A square. Now rearrange this one here, V final B square equal to half V final square A, or V final B equal to 1 over square root of 2 V final A, or in other words, V final A equal to square root of 2 V final B. Two cannonballs are dropped from a second floor physics lab at height h above the ground. Ball B has 4 times the mass of ball A. When the balls pass the bottom of the first floor window at height h over 4 above the ground, the relation between their kinetic energies Ka and Kb is, now again from the conservation of mechanical energy, E final equal to E initial, and K final A in this case here, plus mgh over 4 equal to ma, this one here, ma gh, no kinetic energy at the beginning here, so the initial kinetic energy it's equal to 0. And from this one here, the kinetic energy Fa equal to, you move this back in here, you will get 3 over 4 ma gh. Same rule for the other particle, the kinetic energy, final kinetic energy of B plus 4 ma gh over 4 equal to the initial position, it's 4 ma gh. Again, no initial kinetic energy here, so K final B equal to 3 ma gh. You divide these two equations, you will get K final B divided by K final A equal to 4. In other words, K final B equal to 4 K final A. That's it. Thank you for watching.